This is problem 111 from chapter 15. In this problem, a box having a weight of 8 pounds is moving around in a circle of radius 2 feet with a speed of 5 feet per second while connected to the end of a rope. If the rope is pulled inward with a constant speed of 4 feet per second, determine the speed of the box at the instant RB is equal to 1 foot. How much work is done after pulling in the rope from A to B? Neglect friction and the size of the box. So initially the box is moving in a circle, and so we have the velocity given here. If I use cylindrical coordinates here, this is the radial direction, this is the transverse direction. And for my angular momentum, angular impulse equation, I have my angular momentum given here, my angular impulse given here. Let's go ahead and rewrite equation 1518 using equation 1513 and the equation that I have here. So I have the initial angular momentum, which is R crossed with mv, and R is going from point O to point A. This is the position of A with respect to O. So for my angular momentum, I have RAO crossed with the mass times the velocity at point A plus my angular impulse, which I have here. To find that, I have to find the net force acting on the object. I have a normal force, which is pointing upward, and a force of gravity, which is pointing downward. The net force in the vertical direction is equal to 0 because those forces balance. I also have a force which the cord exerts on the block, which is pointing inward, like this. But if I do R crossed with that force, I get 0. That's true not only at point A, but at every point along the way. So when I'm at point B, the force that the cord exerts on the block is pointing inwards, but my vector now, this would be the position of B with respect to O, is pointing in the opposite direction. So this cross product is always going to be equal to 0. So the angular impulse is equal to 0. So the initial angular momentum must equal the final angular momentum. My final angular momentum is R B with respect to O crossed with the mass times the velocity at point B. I'm looking for the speed at point B, so I'm going to find that using the velocity here. When I do this cross product, if I'm looking downward at point B, so this is looking straight down, I have a component of the velocity which is pointed in towards the center of the circle. That's going to be the 4 feet per second width, which is the speed that the cord is being pulled at. And looking straight down, this would be the transverse direction, so I also have a component in the transverse direction. This is the radial component. It's pointing inward, so the radial component would be negative. So we can write the velocity at point B is equal to the radial component, and remember VBR is negative, plus VB theta, maybe I should call this -4, VB theta in the transverse direction. So I could also write this as my vector R crossed with M times VBR in the UR hat direction plus VB theta in the transverse direction. Or if you wanted to use rectangular components for this cross product, you could say at point B, this would be in the I hat direction, this would be in the J hat direction. This vector is in the same direction as the radial component here. So if you call that the I hat direction, you have I hat crossed I hat here, which is 0. So this term does not contribute. And then we have the magnitude of this vector, which is 1 foot. Let's just call it 1, times the m, times the VB theta. If you call this I hat and this J hat, you have I hat crossed with J hat would give you K hat, or if you want to stick with cylindrical components, this is in the radial direction, cross that with the transverse direction and you get something pointing in the Z direction. And then on this side of the equation, you have your R vector pointing in the radial direction, your 5 feet per second is pointing in the transverse direction. Those vectors are perpendicular to something. They also give you something pointed in the Z direction. This is the magnitude of the R vector, which is 2 feet, times the mass, times the velocity at point A, which is 5. Have the mass on both sides of the equation, so that cancels out. This is the Z component, this is also the Z component, so those two components must be equal to each other, and I get 10 is equal to 1 times VB theta. I was asked to find the speed when RB is equal to 1. Well, this is just the transverse component. So to find the speed, I'd say this, you can see from what we have up here. So the speed is equal to VBR squared plus VB theta squared. Well, we're squaring the radial component, so it doesn't matter whether it's positive or negative, but it is pointing inward. So it's negative 4 squared plus 10 squared, and that gives me 116. Take the square root, that gives you 10.77 feet per second. Okay, so then we also want to find the work that's done. There's two ways that I can find the work that's done. I can use the definition of work where I'm doing an integral here, or I can just say the work done is equal to the change in kinetic energy if I bring the T1 over to this side. So that's what I'm going to do here. So the work as I go from A to B is equal to the kinetic energy at point B minus the kinetic energy at point A. Now, I have the speed at point B. I have the speed, this is the speed at point B. The speed at point A was equal to 5. This is equal to, the kinetic energy is 1/2 times the mass times the velocity squared. So this is 1/2 the mass times VB squared minus 1/2 the mass times VA squared, or you can say 1/2 the mass times VB squared minus VA squared. VB is 10.77. If you square it, you get the 116 back again. So this is 1/2 times the mass times 116. VA was 5. 5 squared is 25. And the mass times G is equal to 8 pounds. So this is 1/2 times 8 divided by G, which is 32.2. And this is 116 minus 25. That gives us 11.3, and the units for work are pounds. So that concludes problem 111.